So Newton comes up and he gets this apple. You know the thing with Newton and an apple. And he takes a pen and he stabs it through the middle of the apple. Like that. And then he starts doing experiments. Like one thing he does is he takes the apple and he swings it like this. So he's causing the apple to rotate about some center point. So we could say that most of the mass of the system is on the end, and I'll draw a little sketch of this apple system for you. Here's our axis of rotation, and here's our apple out here. That's a nice picture of an apple, right? And so we could say that the apple at this instant is going, I don't know, let's say the apple's going that direction in this rotation. Of course, the tangential speed's always going to be normal to the axis of rotation. And we know that we're probably going to label this distance here ara, and we're probably going to say that the speed, what is the speed? I guess it's going to be r times omega. Hope all that stuff is okay with you. Now I want to think about what the kinetic energy of this system is. What is the kinetic energy of this system? We know that kinetic energy is 1/2 mv squared. And we can plug in what v is because we know that it's r times omega, and that's going to be 1/2 m times r omega square. And if we spread this out a little bit more, we can say that it's 1/2 m r square times omega square. And the reason I'm doing this is I'm going to identify this thing as something cool. Here we go. Something cool. So our plan is to take this equation, 1/2 mv squared, and make it into a rotational equation. This something cool that I want you to recognize is, well, you don't have to recognize it yet, but this is called the moment of inertia. Moment of inertia is the standard name for this thing, but I'd like to call it something else. I'd like to call it rotational inertia. So we'll put a little or here, and this is my personal preference. And I'd like to tell you why we can call it rotational inertia. The moment of inertia, again, is what it is typically called, and it's got this variable I that's associated with it. We could call it a capital I. Here you go, capital I, moment of inertia or rotational inertia. Now I want you to look at these two equations. We can say that linearly and rotationally, we can compare these two kinetic energy equations. You've got K equals 1/2 mv squared, and over here you've got K equals 1/2 I times omega squared. So this is 1/2 in both of the equations, and this is, well, let's look at this V thing. This is speed, and this is rotational speed or angular speed. Velocity, angular velocity, and it's square in both the equations. And so here we've got mass in the linear side and rotational mass or rotational inertia in the rotational side, the angular side. So I hope this equation makes sense to you. In principle, if you consider this stabbed apple and the apple is rotating about some fixed axis, we could in general call anything where anything that is spinning, even Newton himself, we could define him as a whole bunch of little fixed masses at certain distances away from a central axis that are rotating. And notice that all of Newton has the same angular speed. See that? He all has the same angular speed. Not all the same linear speed. Not all the same rotational speed, because ara is different. So Newton's hair is moving faster than Newton's bow tie, but all of Newton has the same rotational speed. That's that omega. So if we can find this I in principle for a larger object, then we can define the energy that's present in something that is spinning. Before we do that though, I want to show you something that is spinning. Here we go. This is a glorified yo-yo. We've got an enormously massive metal disc with a marking on it so you can kind of measure how fast it's spinning. You might be able to do video analysis with that. And I'm going to go out a little bit and let this sucker loose and we can study what's happening. It's spinning faster, faster, faster. When it gets to the bottom, it's spinning really fast. But the reason it goes up, again, after reaching the bottom, is because at the bottom, it's got some energy. Just like a yo-yo. And you know that if you're using a yo-yo and you tighten the yo-yo string at the bottom, while it's spinning at the bottom, you tighten the string, it'll climb back up the string. Give it a little tug, and it'll go. So this proves to us that things that are rotating have energy, and that energy can readily be exchanged for gravitational potential energy. That's why this disk is rising back up again. Okay, I just argued verbally that we could take something, any object, let's put an axis on it, and make some blob-like object, and cause it to spin around with some omega. Here we go. Let's go out to this chunk, this little chunk of object right here, and say that the distance for this particular chunk of object is ara, and if it's rotating with some omega this direction, then the velocity at that instant is that way, at a right angle to the ara. And we could treat this object as a very large number, a very large number. We're hinting at calculus here, a limit as these little chunks become smaller and smaller of the object. And we could spin this thing around and we could treat it as a very large number of systems like this. So let's set up a sum. We're going to not do it quite calculus way yet. We're going to say that the kinetic energy of the whole is the kinetic energy of all of the parts. And so we'll take a sum of 1/2 the mass of some individual thing. Then I'll use this index I, and we'll use I from, well, we can label them starting from 1 to the total number of particles that are inside this thing, which in principle could be very large. This is not a problem you would want to ask your little brother to do. And this is the kinetic energy equation, and we're going to say there's a kinetic energy of every single one of those parts. But again, we know how fast each of these parts is going. It depends on how far each chunk of this rotating blob is from the axis of rotation. So let's put ourselves another sum right here. We're going to go from I is 1 to n, and we're going to say that this is 1/2 the mass of the chunk times, now instead of putting the velocity, I know that velocity is r times omega, so it's the radius to that particular chunk times the omega of that particular chunk square. Radius is also going to be square because we're supposed to square the whole velocity right here. So I want you to think about omega. We said that the object itself has an omega, so we can write this again where omega doesn't have an index. And I'm actually going to pull omega out of the sum. Also, we can pull 1/2 out of the sum. Watch this. This is equal to 1/2. It's just like an integral. When something is a constant, you can pull it out of the sum. Now I'm going to take a sum. I is 1 to n of 1/2. The half is already gone. mi ri square. That's inside my sum. And then outside my sum is omega square. Now I see this is 1/2, look at this, rotational inertia, is probably this thing that I can underline in blue. Look at this right here. This thing, I've got 1/2 omega square times this thing right here. I better identify that as I. This is 1/2 I omega square. So now I've got a definition of I. I could put it over here. The moment of inertia of any object. This is a wonderful thing. This is how much something resists beginning to rotate. It also would be how much something resists. Excuse me. Wow. Excuse me. It is also how much something resists stopping rotation. So it has to do with the mass and how far away the mass is. But you notice that the mass being far away has much more of an impact on the rotational inertia, I, the moment of inertia. It has a much greater impact when the mass is far out from the axis than it does just that there's more mass. So there are two disks right here. I can show you them in just a little bit. But this is the idea. And of course, I has units. The units of I are the units of things that make it up. It's kilograms times meters squared. Kilogram meters squared. So I resists angular acceleration. And we'll get a couple more equations for it in just a moment. But I want you to consider these two objects. They have the same mass, and the mass is distributed very differently. So which one do you think would have a large I? I'll push them up here a little bit. If the mass is the same, and we've got this equation for I is equal to, well, we have to add up all the masses. It goes from I is 1 to the total amount of mass of the thing, of the mass at some particular location times the location squared. So in which one of them is the location always going to be big? Yeah, this one right here. This one has a very big location for every bit of mass because it's all at the same total radius for the ring. But this one has a whole bunch of mass in here. The mass that's in here, being so close to the rotational axis, doesn't have much of a contribution to the moment of inertia. The mass that's out here does, but notice there's a lot of mass that's close in. So this one will be easier to start to roll than this one. What about a bike tire? If I leave that for you. What do you think? Bike tire, large moment of inertia or small moment of inertia? What about an apple rotated like this? Large moment of inertia, small moment of inertia. Interesting, interesting. We can get a whole bunch of special cases and write them down, shall we? Let's just do it. I'm going to find the moment of inertia of a hoop. Or we could call it a ring. Here we go. What I need to do, it says I need to go from 1 to n of all the little bits of mass in this ring. And that's the mass times where the mass is located square. So if I put the axis of rotation here, and I draw myself a little arrow vector, I notice that all of the mass is located at the outside. So this equation becomes a little bit simpler. I'm going to say from the beginning to the end of the mass of each section times the radius of the ring square. Notice that that does not any longer depend on which chunk of mass we're talking about. The reason is all the mass is at the very edge. So this becomes even simpler. It's just r square times this. I is 1 to n of all the mass. This instruction right here says add up every bit of mass from the beginning to the end. What is all the mass from the beginning to the end? Ooh, let's be more careful. I'm going to be more careful. I'm going to call this a capital R so we don't get confused. The capital R is the total radius of the ring, and this is a capital R to show that we don't care about the distance. It's always this largest R. And I'm going to make this a capital R also as a result. So this says add up all the mass and don't do anything to it, just add it all up. So you know what that is? That's the total mass. So this is the total mass times the total radius square. And that, you'll find, is very, very interesting. It's the same, remember this? It's the same as a single mass, maybe I should throw this up here. It's the same as a single mass rotating around some fixed point with a massless axis on it. It's the same as this apple going like this. If all the apple's mass is concentrated at one point. Okay, so this is a super useful equation that you will probably want to memorize. Do it. Want to do a disc? Let's do a disc. This is a little bit of a different problem. A disc has mass in the middle also, and I'm going to find its, let's see, we've got ara. Let's start from here and go to here. That's capital R. And we're going to say that I is equal to the sum from I equals 1 to the total number of mass chunks in here of the mass times where that mass is square. And we could say that most of the mass of the system is on the end, and I'll draw a little sketch of this apple system for you. Here's our axis of rotation, and here's our apple out here. That's a nice picture of an apple, right? And so we could say that the apple at this instant is going, I don't know, let's say the apple's going with you. Now I want to think about what the kinetic energy of this system is. What is the kinetic energy of this system? We know that kinetic energy is 1/2 mv square. And we can plug in what v is because we know that it's r times omega, and it's going to be that direction in this rotation. Of course, the tangential speed is always going to be normal to the axis of rotation. And we know that we're probably going to label this distance here ara, and we're probably going to say that the speed, what is the speed? I guess it's going to be r times omega. Hope all that stuff is okay. 1/2 m times r omega square. And if we spread this out a little bit more, we can say that it's 1/2 m r square times omega square. And the reason I'm doing this is I'm going to identify this thing as something cool. So Newton comes up and he gets this apple, you know the thing with Newton and an apple, and he takes a pen and he stabs it through the middle of the apple, like that. And then he starts doing experiments. Like one thing he does is he takes the apple and he swings it like this. So he's causing the apple to rotate about some center point. So